Hello and welcome to this video about determinant proofs. In this video we'll prove this theorem, that a matrix multiplied by its adjoint on either side is equal to a diagonal matrix with all of its diagonal entries being equal to the determinant of A. So now to discuss what an adjoint is. We'll set matrix A to be this matrix with these entries. The adjoint of a matrix is a matrix containing all of the cofactors of this matrix corresponding to these entries. This is what a cofactor is. It's equal to the determinant of the corresponding minor of this matrix, multiplied by 1 or minus 1, depending on what the subscripts are. So I'll just scroll everything up the screen here to make some more room. And this is what the minor of A is at position row I and column J. It's matrix A with row I and column J removed. I've explained minors and cofactors a lot more in the previous video on the cofactor proof. So now to prove part A of this theorem, which says that AB is equal to BA on this condition, that they multiply together to make a matrix that's a scalar multiple of the identity matrix. So now to start this proof, we'll start with the first given equation. We'll multiply this equation on both sides by inverse B on the right. The left-hand side will simplify to give A on its own. The matrix inverse B can move to the front because of various theorems used together. It can move past both the identity matrix and then the scalar. We can multiply both sides by B on the left this time. And after simplifying the right-hand side, we get the second equation that we're trying to prove. So we've proven part A of this theorem. So now to prove the main part of this theorem. We'll start with the first expression and expand it out using IJ bracket notation. The adjoint of A is a matrix filled with the cofactors of A. We can expand it out into a larger matrix notation with dots because we're uncertain as to what size it is. We can evaluate the transpose of the second matrix to get this matrix with its subscripts flipped. We have to multiply these two matrices together, so we'll have a go at multiplying row I of the first matrix with column J of the second. We'll get this sum after we multiply them out for this particular entry ij. Then we can write it in sigma sum notation. We can then use a past theorem to write it out like this. And this is equal to the determinant of A multiplied by the identity matrix. So we've proven it true for the first expression. Now we have to prove it true for the second. Now to prove it true for the second expression, I'll just start with a fairly clean screen. We can use part A of this theorem to prove it true for the second expression. So we'll invoke it and substitute the expression in for the variables that we have to prove it for. A will go in unchanged. So we can say from part A of this theorem that the second expression is true. So that's it, we've proven this theorem. So I hope that you found this video to be helpful and educational. Please click like and subscribe if you did. Feel free to write anything helpful in the comments and to share this video, and thanks a lot for watching.